Okay, so today we take a small break. We have seen a few examples of problems, a few hints of the general structure of the theory, but I would like to take a break and revise with you what we have somehow learned, what's quantum mechanics about. Okay?
Sorry, do we have to record?
Yeah.
Yes.
I pressed it. Is this up?
Ah, okay, yeah.
Is this recording? Okay. So, let me just give a slightly more abstract formulation for states and operator. Okay? So we said we need some Hilbert space. Okay? The example that we had in mind was space of functions. Okay? So in that Hilbert space, if I have two functions, okay, the scalar product was what? The integral over space of psi star of x times phi of x. Okay? That is obviously, in order for this to make sense, the integrals have to converge. And for instance, to calculate the scalar product of a function with itself, which is essentially the integral of the psi x modulo square, this integral has to converge. Okay? And typically one says that the space is called L2, which means that the second, this is called the L2 norm. Okay? This integral converges. Okay? So this object is less than infinity. We discussed subtleties like the fact that plane waves, which are useful, do not belong to this space in the infinite volume and so on and so forth. But this is an example of a Hilbert space. Now, a simpler example. Let us consider vectors of numbers, phi1, phi n. Okay? Now, I want these numbers to be complex in general. Okay? So this is not r to the power n, but rather c to the power n. Okay? Simply column vectors of complex number, phi I belonging to c. N of them. Is this a Hilbert space? Yes, it is, because somehow it's a finite dimensional Hilbert space. In fact, easier than this. So this is a finite dimensional Hilbert space. Okay? How do you define a scalar product? So if this is, by definition, my vector phi, these are the components of the vector, okay? You see, I'm still using this cat notation, but now I mean just a column vector. Now, how do I define the scalar product of two vectors, so psi and phi? Well, I simply take the sum over all components of psi j star phi j. Okay? Pretty much as you would do for, in Euclidean space. In Rn, you would do exactly the same, except that here there is no need for the complex number, right? If I want the norm of a vector, it's just the sum of the square of the components of a vector. If I want the scalar product, it's precisely this. Is it clear? Okay? Okay, so this is the second example. Infinite dimensional example, finite dimensional example. Now, generally, okay, you say that on a Hilbert space you must be able to define a scalar product, okay? So in general, you must be able to define such an object, okay? So a Hilbert space is somehow a vector space, in the sense of linear algebra, space of vectors that you can add and so on and so forth. Complex in general, okay, so be ready to complex numbers, where you can define also a scalar product, as we have seen in the example before, and the scalar product have to have 4 properties. First, well, in general, this object belongs to C, so it's a complex number, and by the way, this object is equal to the star of the opposite object. You see from here, every time you switch the two things, you get the star. This is, by the way, very useful because if you take the same object, you realize that it's real, okay? And in fact, we'll see in a second what this implies. Okay, so property B is in fact exactly what I announced there. So phi psi should be equal to psi phi star. Okay? Property C is that this scalar product must be linear in the argument there. So if I have psi C1 phi 1 plus C2 phi 2, okay? I make linear combination of two vectors with two complex numbers C1 and C2. That is equal to C1 psi phi 1 plus C2 psi phi 2. Okay? Where these are complex. I don't write it. The third requirement that you make for a scalar product is that psi, which as I told you must be real, is also non-negative. Okay? And in particular, equality only if psi coincides with the zero of the Hilbert space. Any Hilbert space being a linear vector space has zero belonging to it, because you can always multiply a vector by the zero of the complex number and you obtain a vector 0. Okay? Is it clear? Okay. So, linear algebra together with a scalar product, complex scalar product, which obeys these 4 things, makes essentially your space a nice Hilbert space. Notice that I have required linearity for the argument there, but since you can always switch the two arguments, okay, by paying a price there, there is also some kind of linearity also on the other vector. But careful, there is a star appearing. So if I do the following, C1 psi 1 plus C2 psi 2 phi, then the result is C1 star psi 1 phi plus C2 star psi 2 phi. Okay? It's very simple to prove. Try to do it. Okay? But you should notice that somehow there is a star paint on the left. Okay? So in some sense, this is often called anti-linearity. Okay? Linearity requires somehow that the constants are exactly the same. If there is a star, it's called anti-linear. But this is name. Now, this property D is particularly important because it allows you to define the length of vectors. Okay? Since this object is equal to 0 only for the 0 vector and in general is positive, it makes sense to define the length of a vector from the scalar product in the following way: psi modulo square equal to psi psi, or in other words, the length of a vector equal to the square root of the scalar product of the vector with itself, precisely as you would do on the plane with the Euclidean vectors. Okay? Fantastic. Further property properties of this scalar product can be shown. For instance, you can prove a triangle inequality. Triangle inequality. Okay? Like the norm of psi plus phi, okay, is less than the norm of psi plus the norm of phi. Okay? It's called triangular inequality for a very obvious reason. If I have two vectors, okay, and the sum of the two vectors, okay, the length of the sum is less than the length of this plus the length of that. Okay? And this is pretty general, okay, for any. And there is also another inequality, which is called the Schwarz inequality. I write it here. Schwarz inequality. It tells that the scalar product of two vectors modulo square is less than the length of the two vectors multiplied together. Okay? Which is, by the way, the length, okay, written as a scalar product or as a length. Now, what is this? Well, you know that you can obtain the scalar product of two vectors, on the plane, for instance, by multiplying the length of one times the length of the other times the cosine of the angle in between. Okay? So obviously the cosine being between -1 and 1, if you take the square, the scalar product square is less than the length of the two vectors. Is it clear? Okay? This is for ordinary vectors on the plane or in Rn, in n-dimensional Euclidean space. Okay? And that's exactly the same thing. So it's, in some sense, you should recall it as the fact that the cosine cannot be larger than 1 in modulus. It is a very general property that can be demonstrated. Okay? Clear so far? That's the structure of any linear vector space, be it finite dimensional, infinite dimensional, equipped with a scalar product which satisfies these things, and therefore also triangle inequality and Schwarz inequality. You can call it a Hilbert space. Okay? And here are two simple examples to visualize what I told you. Okay. Good. Let's proceed. And so I eliminate here the definition. As in linear algebra, if I have a set of vectors, phi j, so more than one, okay, a word about the notation. You have seen, sometimes I write the vector as phi, sometimes as phi, with the cat notation, okay? Mathematicians certainly don't like this, okay? So if you go and look in a book of mathematics, they would call an element in the Hilbert space, say, like this, or whatever symbol they want to use. Not like this, okay? Nevertheless, if I write phi without anything else, there is a possible confusion with just the components, for instance, of these vectors. You see? So, the vector itself and the components, for instance, here in the n possible coordinates, should be clearly distinguishable. Okay? So whenever there is a possibility of confusion, I stick to the cat. Okay? So that it's clear that this is not. So for instance, if I write like this without the cat, you might be puzzled and say, what is it? A complex number? No, this is a vector. Okay? So each one of these, for instance, if I'm thinking of this, has n components, okay, which I should add with an extra label, right? Okay, so suppose that I have a set of vectors in the Hilbert space, okay, so this is all vectors in the Hilbert space. I say that these are linearly independent if, when I form the sum with complex coefficient, the result is 0 only if all coefficients are 0. Okay? You remember that this is the standard definition of linear independence of vectors from linear algebra. It's the same in infinite dimension, whatever. Okay, so this is the linear independence. The other important property is usually orthonormality. Okay? You say that the set is orthonormal if phi j prime, say, phi j, I said I take two elements in the set, and the result of this thing is the delta of j prime j. Okay? Kronecker delta. So it is equal to 1 if I take the same element, 0 otherwise. Okay? This is an orthonormality condition. Alright? Okay. Now, let us demystify a little bit the bra. Remember that there is the strange thing that somehow one define also this object here. But so far I haven't used it. I mean, this is a notation for a scalar product. There is no such a thing as this. What is the meaning of such a thing as introduced in some sense by Dirac? Okay, let us define a linear function. Suppose that I have a linear functional. Linear functional. So I want some function from the Hilbert space into the complex number. This is what you call a functional. So something that takes a vector and associates to it a complex number. Okay? And I want it to be linear. Which means that if I take f and I apply it to a combination of two elements, okay, the result is C1 f C1 plus C2 f C2. Okay? This is by definition a linear functional on the Hilbert space. Is it clear? Fantastic. Have you seen one already?
The norm or something like that.
The scalar product is a linear functional. Okay? Take any psi, okay, and consider f somehow given by this psi of phi being psi phi. This precisely satisfies the condition of being a linear functional, right? Because it takes any vector and associates to it a complex number. Fantastic. Next is linear in this argument. We specified that the scalar product should be linear. Okay? So that's a linear function. We have seen one. Okay? You invent any psi and associated to that there is a linear functional. And now comes, you might ask, are there any other linear functionals except this? And the answer is a nice theorem. It's called the Reach Theorem, which is kind of a representation theorem. It tells whatever linear functional you can think of, there exists essentially a psi such that you can represent it in this way. Okay? So these things that you have seen somehow exhaust the possibilities of linear functionals. Okay? So in this sense, whatever functional f of c, there exists some vector f in the Hilbert space such that you can write f of phi as the scalar product of f with phi. So in this sense, somehow you make sense of this object. This is something waiting for a vector to take the scalar product of, okay? But in actual practice, this is the functional, the linear functional associated to this operation, okay? So it's not a vector in the Hilbert space, but it's related to a vector in the sense that you can take scalar product with any vector and this defines a linear functional. Is it clear? Okay? As simple as that. That's a bra. Bra is waiting for something. Okay? So it's essentially what is written there in the scalar product. So this is called Reach Theorem. Okay? You can always find. Notice, do not confuse linear functional with linear operators. They are different. A linear operator A, okay, is first of all something that given a vector associates another vector. So, okay? So it's not something that gives you a number, a complex number. It gives you another vector, and obviously the linearity is the same. So A associated to C phi1 plus C2 phi2 indeed is C1 A phi1 plus C2 A phi2. Okay? But hopefully the distinction is clear. These are vectors in the Hilbert space. These are numbers. Okay? Good. So far it's clear? Okay. Okay, let us return for a second.
Can I ask a question?
Yeah.
Which one is functional? Is it the bra or the dot product?
The functional is the association of this to this number. Okay, so somehow the functional is the fact that you can take a vector and associate to it a complex number, which is this thing. So it's the dot product in some sense. Scalar product is the functional. But in some sense you have you can choose whatever psi you want here. Okay? So you change psi and the functional changes. And vice versa. For any functional, if it is linear, you can sort out that there must be some vector such that with that vector you take the scalar product. Okay? So it's a one-to-one relationship. Is it clear? I don't know, it's more complicated to say than to just stare. It's a completely trivial thing. Okay? It's just a shift of the way you look at things. Okay? Okay. Let us insist on the finite dimensional case again. Now, infinite dimensional Hilbert space are tricky, always tricky. Okay? Finite dimensional cases are somehow very relaxing because everything becomes just a little bit more complicated than linear algebra you have done in school. Okay? And in fact, a lot of quantum information, okay, is based on finite dimensional realizations. Okay? So you can do a lot, really, in quantum mechanics by just ignoring the difficulty associated to infinite dimensional Hilbert space. Just think of a finite dimension, because, I mean, certainly, if you want to study something on a computer, you better have some finite dimensional problem to put on the memory of your computer, and not certainly an infinite dimensional one. Okay, so let's concentrate on the finite dimensional case. Okay, now let me assume that I have in this finite dimensional space an n-dimensional, so I will call it small n here, I don't know, n-dimensional case. Okay? I have an n-dimensional basis, and for reasons, let me call it uj. So j goes from 1 to n, okay? And this is an orthonormal basis. Okay? In precisely the same meaning I explained before. Okay? So, in terms of this object, you can express any vector in the space. Okay? You take a vector, phi, and you can rewrite it as a certain combination with complex coefficient phi j of the basis vector uj. Okay? How do you calculate the coefficient? Okay? Suppose that I tell you, okay, take this vector, express please in terms of the basis. How do I calculate the coefficient?
With the functional
The trick that we have used.
Scalar product.
Scalar product, okay? So it's always the same trick. So if I take here the scalar product of this with uj, say, prime, phi, okay? This is equal to the sum over j, phi j, uj prime, uj. But you know that this is an orthonormal basis, so this is a delta, j prime j. So of all the numbers here, only one counts, and this phi j prime, okay? So this object here is nothing but the projection of the vector phi on the element j, okay? Very good. So in some sense, discussing about abstract vectors in the space or as its components is almost the same thing. Once you fix the basis, you can represent vectors in the space as components with respect to the basis, right? Which means that I have reduced myself to somehow the example I've given here, okay? So it is essentially a column of components in Cn that I have to handle, okay? For any given basis. If I change the basis, the representation of the same vector changes, obviously. But once I fix a basis, an orthonormal basis in particular, discussing about a finite dimensional Hilbert space or Cn is precisely the same thing, essentially, okay? If you want to be fancy, we have established an isomorphism between the two things, but this is just names, okay? Now, this is for vectors. What about for linear operators? Can I still do the same trick for linear operators? In other words, can I represent linear operators in terms of something simple? Here, I represent a vector in terms of a vector of components. Linear operators, I will show in a second, can be represented as matrices. Okay? Let's see why. Okay. So, I take first of all a linear operator and I apply it to an element of the basis, uj. Remember, I've selected the basis. Okay? Now, this is certainly equal to some combination. Since this is a vector in space, it must be some combination of the uj prime with some coefficient, okay? Now, the question is, how do I obtain the coefficients? And again, the trick is almost the same. Take the scalar product of this thing with, say, uj prime, and you realize that the coefficient that you need here is precisely uj prime a uj. Okay? Pretty much as here. Okay. But this is a matrix. Okay? This is the matrix representing the operator in the given basis. n by n. Fantastic. I will show you now that this is enough to express the action of the operator on any vector, not only on the element of the basis. Obviously, what I need to use is linearity. Okay? So let's do it. I take A and I apply it to phi, a vector in the Hilbert space, which is a combination of uj. This will give me some other vector, psi. Remember, this is a linear operator, and so it sends an element phi into an element psi. Okay, let's do it. Now, phi is written here. It's a combination of the basic elements. Okay, so this is equal to A applied to sum over j of phi j uj. Right? But this is a linear operator, so this is equal to the sum over j of phi j. I can take it out. This is a constant. Times A applied to uj. Okay? Do you follow? But A applied to uj, I told you it is equal to, so here I rewrite sum over j, phi j. This is equal to the sum over j prime. I don't put the limits. It's, when I write the sum, it's between 1 and n. Okay, it's a finite sum. And this is equal to sum over j prime of uj prime times the matrix element j prime a uj. Okay? Let us rearrange a little bit this object here. I rewrite it in the following way. Let me define, I write it like this, sum over j and j prime, both of them, and then I write it as u j prime, it's here, and then I have the u j prime a u j times phi j. I simply move this a little bit further down, okay, and let me call this psi of j prime, okay. So in the way I have written it, this is equal to, sorry, it is a little bit, unfortunately, there is a, yes, there is here a sum over j inside, okay? So in the notes it's written slightly wrong, okay? So I write like this, the sum over j prime out, and then I write the sum over j in here, and I call this sum here psi of j prime, because j has been summed over. So in this last form, I have written it as psi j prime u j prime. Okay? Now, evidently, this is the expression of the vector psi in terms of the basis, right? So all in all, I have shown to you that if I have a certain expression for the vector phi in terms of the basis, correspondingly, if this is the abstract way of writing the operation, the operations in terms of vectors and matrices is simply the following, that psi j here is equal to, or psi j prime is equal to sum over j of u j prime a u j times phi j, summed over j. Okay? So in other words, the column vector of the psi is equal to the matrix of the A times the column vector of the phi, in the usual matrix product way. Okay? So, end of this little story. When I have a finite dimensional space and I fix an orthonormal basis, working with vectors and linear operator is precisely the same thing as working with column vectors and matrices. Okay? So this is called the representation of the operators and vectors in the given basis. But I can choose whatever basis I want, by the way, okay? As long as it is orthonormal. Clear so far? Fantastic. Now, let us consider an exercise that we have already done. Remember the harmonic oscillator. Okay? I have shown to you that I can define function phi n of x being normalization constant times polynomials that are, by the way, called Hermitian polynomials times e to the minus x squared divided by 2. If you want x to be with dimension, put the oscillator length explicitly. Okay? So this is x is now the coordinate with the dimension of a length. Okay? These functions are orthonormal functions. You can prove. So in some sense they form a basis of the space of functions. So in 1D, in one dimension, space of one-dimensional coordinates, they do have here, this would be the analog of that uj. You could call it phi n. Okay? Probably is unfortunate. Let me call it u. Okay? I call them phi in previous lecture. Now, for me, this is an element of a basis, phi un. Okay? And how many of them I have? Well, n can be anything from 0 to plus infinity. Okay? So I have really not a finite dimensional Hilbert space, but an infinite dimensional Hilbert space. Obviously, in the end, this is nothing but a basis of L2. Okay? So I need an infinite number of elements of Hermitian polynomials to represent an arbitrary function. Right? Nevertheless, if you allow me to somehow switch gear a little bit and take this not so trivial limit in general and going to infinity, now I have a basis, an infinite basis, on which I can represent anything I want. Okay? For instance, suppose that I ask you, please represent the operator x. Okay? What do I do? Well, you remember that x was, apart from the length L over square root of 2, a plus a dagger. Right? So, suppose that I ask you, calculate any matrix element appearing here. Okay? So, for instance, u and prime, I insist in calling u, but if you want, you call it phi. The only thing I wanted to avoid is making confusion with the components of the vectors. Okay? So these are full vectors in the Hilbert space. U and prime L, so U and prime X, U n. Okay? How do I calculate this matrix?
Using the
Right. First of all, writing the necessary ingredient, which is this: A plus a dagger, U n. How do I calculate the matrix element, for instance, of A?
using the properties of raising and lowering. Yeah.
A U n is equal to the square root of n u n minus 1. A dagger u n is equal to the square root of n plus 1 u n plus 1. Okay? So this matrix is in principle perfectly coupled, square root factors. Okay? Obviously, so it's not diagonal. There are elements outside of the diagonal, and it's an infinite matrix. Okay? So I could call it somehow the matrix X n prime n, okay, is the matrix representing the operator X in this basis of A plus P. Okay? Another operator, P. Okay? So I take now the operator P, which is, well, H bar over L, 1 over square root of 2i, A minus A dagger. Okay? Obviously, same trick. I can calculate the matrix associated to P. It's an infinite dimensional matrix, which I calculate with the same ingredient almost. Okay? So I can do quantum mechanics working with matrices. And needless to say, if I take a properly defined commutator of these two infinite dimensional matrices, what I obtain is I H bar times unity. Okay? This matrix formulation was precisely what Heisenberg invented. Okay? So he understood that if you work with matrices, then you can define a quantum theory. On the opposite side, Schrödinger worked with wave functions. So at the beginning, for a very short time, this seems to be as two independent formulations of quantum mechanics. Okay? But then Schrödinger himself was able to show that indeed you just need to represent functions on a basis to get Heisenberg formulation. Okay? So the matrix formulation and the wave function formulation are two aspects of the very same basic theory. Is it clear? Good. I'm going slowly because somehow there is no point in revising the theory and just flashing it too fast. But if this is still not enough, careful, please stop me. Okay, is it clear so far? Okay, now let us discuss a little bit more about Hermitian operator and their spectral representation, because this will be also useful later on. So, Hermitian operator and their spectral representation. Okay. Given an operator A, linear operator, we always discuss about linear operators, okay? I can define what is called the Hermitian conjugate, which is denoted in the following way, by the following characterization, okay? Given any two vectors, phi and psi, in the Hilbert space, you pretend that the action of A on phi, scalar product with psi, is reproduced precisely by the action of any of this adjoint operator on psi, scalar product with phi. Okay? In other words, it is the operator that you need to put here if you want to move this. Okay? This is the Hermitian conjugate in general. Is it clear? Okay. Now, I could write this, as I told you before, democratically in the Dirac notation by this. Okay? So I add an extra bar. So this is the action of A on phi. Here I see as A in between these two vectors. Again, I remind you of the meaning of this bra. This is scalar product of this. Okay, Is it clear? This is the definition of Hermitian conjugate in general.
I have a question.
Yeah.
The phi and psi are members in the Hilbert space. But
Yeah.
do they have the same eigenvalues when A is operating on them?
I'm not discussing yet about eigenvalues of A. Okay? This is something that has nothing to do with the eigenvalues of A. Plus, I mean, obviously, these are not eigenvectors of A. Any vectors in the Hilbert space. So forget about what are the eigenvalues of. They might be not eigenvectors of A. Okay? In fact, I have not even discussed if A has eigenvectors or not. Okay? I just define any linear operator, I can define the adjoint. The adjoint is what I have to put on the left somehow to make this equality true. Okay? This is the definition. By definition is what I have to use here in order to reproduce the action of A on the right, however. Okay? And we have seen it in action, for instance, for P, for instance, when I have P acting on the left, I have to integrate by parts, okay? So it is the same operator in that case, okay? If I have simply the derivative, then I need a minus sign, because integration by parts command that, okay? So this is the object that you have to put on the left to have the equality satisfied. Now, you say that the A is Hermitian, okay, if A coincides with this Hermitian conjugate, okay? So if A can travel back and forth, so I rewrite it. If this is true for any side and phi, then A is Hermitian. Okay? So remember, A can stay here or on the left. There are subtle questions about domains where these two operators are defined in the infinite dimensional space. So the mathematician will say, no, this self-adjoint Hermitian requires. Never mind. Okay? So you can read. There are places where these things are carefully written, but to me it's perfectly satisfactory if we forget about these details about the domain where the operators are defined. In the finite dimensional space, by the way, there is no problem. The issue is on infinite dimensional space. Okay, good. So this is the Hermitian conjugate, and this is an operator that is Hermitian. And I want to show to you two properties that are useful. The first is the following. So first of all, let me just rewrite this in the following way. You see, this is also equal to phi A psi star. I simply have switched the two things. Okay? So an operator is Hermitian if whenever you switch the two vectors, you just need a star. Okay? Look at this two ways of seeing. Okay. Now, property A. A is Hermitian whenever, if A is Hermitian and you sandwich between the same vector, then that's real. Okay? That's pretty clear because, as I told you, if you exchange them, you have the star. But exchanging two things which are the same equal to the star means it's real, right? Okay? So an Hermitian operator has a sandwich between the same vector that is necessarily real. The second property is a bit more complicated. It's called the Spectral Theorem. Okay? The Spectral Theorem says essentially that I can find a complete basis of the space, a complete basis of eigenvectors of A, which generate the Hilbert space. Okay? So, this is a theorem that is slightly more complicated to prove. Okay? For finite dimensional spaces, it is essentially a theorem of linear algebra. You know that if I have a symmetric matrix in linear algebra, I can find a basis of eigenvectors, okay, which exhaust the whole space. I can diagonalize, so to speak, the matrix. Okay? The same thing holds true for an Hermitian operator, which is essentially a symmetric matrix apart from a star. Okay? So, just to tell you, this matrix here, so the diagonal elements are real, and here, for instance, I have I. This matrix is Hermitian. Okay? Because all you have to have is that the off-diagonal matrix are the stars of each other. How do I see that? Okay? Look at the expression that I have there. The elements of the matrix are this. But if the operator is Hermitian, then I can exchange the two just paying the star. Okay? So the elements on the other side just have a star. Okay? So to spot if a matrix is Hermitian or not, you just stare at it. On the diagonal, you must have real numbers. Off diagonal, either a real number, or if it is complex, then the star in the transpose. Okay? Good. Now, the fact that, again, you can find a complete basis of eigenvectors of A if A is Hermitian, it's a theorem of mathematics. Okay? So this is a bit about your question. Is this you can find vectors, okay, such that A, say phi A is equal to A phi A, okay? You see, this is an eigenvector with eigenvalue A. The first thing that you can prove is that A must be real. Okay? Why? Because if you take the scalar product with A, this is just a diagonal element, okay? And therefore, as I told you, the diagonal element is always real. The eigenvalues are real, and you can find a sufficient number of them, either finite, if it is a finite dimensional space, or an infinite dimensional number, to express with these elements any element in the Hilbert space. So this is a basis. Okay? More precisely, is an orthonormal basis. I will not prove this. Okay? This is, I mean, especially in the infinite dimensional case, a very delicate thing. In the finite dimensional space is a variation of a linear algebra theorem. Okay? But it holds true. Okay. Clear so far? Okay. But there are a couple of properties that are simple, and maybe I want to stress them more. Okay? So let me take a short description of this spectral theorem. So let's write this a little bit more closely. Suppose that I have this Hermitian operator and I have some eigenvectors of it. Okay? I will call, say, phi n and a n the associated eigenvalue. Okay? So this is the eigenvector and this is the eigenvalue. Okay? Now, we said the eigenvalue is real. Okay? Essentially because if you take the scalar product with Fn, that's equal to An Fn Fn, but this is Hermitian, and therefore it's equal to exchange the two, Fn A Fn star, and this is 1, and therefore An is equal to its star. Okay? So it is real. Fantastic. But now, let me show you that if I have two vectors, one with An and another with Am, a different eigenvalue, okay, with Am different from An, okay, not the same, a different eigenvalue, then automatically the two vectors are orthogonal. Okay? How do we show this?
Multiply the top one by phi m and the bottom one by phi n.
Several ways of showing. Are you, I mean, is this too trivial for all of you? No. Should we do it? Let's do it. Okay? There are many ways of doing it. Okay. For instance, let's consider the following thing. Let's consider phi m a phi n minus phi n a phi m star. How much should this be? 0, because A is Hermitian, right? So I told you that if you switch and take the star, it's the same thing. So this object is 0. And now I use the fact that this is an eigenvector with eigenvalue An. Okay? So this is equal to An times phi m phi n. Okay? Minus, what about this object here? This is an eigenvector with eigenvalue Am. Okay? So this is Am times phi n phi m star. Okay? Now Am is real. Okay? So you can take it out. So what I write here is An minus Am, and the object that I have here is exactly this, right? Because the star of the scalar product is this. So it's phi m phi m. Is it clear? But this is by definition different from 0, because these are different eigenvalues. So 0 is equal to something different from 0 times the scalar product between the two eigenvectors. Okay? And therefore, the two eigenvectors must be orthogonal. Okay? So that is something simple. What else should I tell you? In general, do not expect that given an eigenvalue there is only one vector with that eigenvalue. There could be a degeneracy. Okay? So you should expect degenerate eigenvalues. And in general, the spectral theorem commands that you find all eigenvectors associated to a given eigenvalue, not just one. Okay? So if this is a degeneracy, you have to find the appropriate number of eigenvectors, and this is enough to form a basis. Okay, what else should I tell you? Well, yes, I want to introduce the concept of the projection operators. Is it clear so far? Okay. This object, I mean, this story is rather dry, I know, but I want to just once and for all to have it discussed. Okay. Now, take an element psi in the Hilbert space. We have already said, suppose that I am in a finite dimensional space, that I can express in terms of coordinates psi n, component psi n, times phi n, where this is a basis in the Hilbert space. Before I was calling it U. Okay, now I assume that I have some basis, for instance, of orthonormal eigenvectors of A. Okay, so the phi n that I discussed just a moment ago. And with that basis, I use it as a basis in the Hilbert space, and I can express any vector. And I know that psi n, the component, is nothing but the projection on the element phi n of the vector psi. Okay? So, if I take this very two simple equation and I write them together, let me just rewrite them in the following way. Psi n times this, but this is equal to phi n psi. Clear? Now, psi is equal to something applied to psi. Okay? So, it is suggested, at least, that this something might be the identity in some sense. But it's also suggested about the possible role that I should give to this object here. So somehow, let me define now an operator Pn being phi n, and now the bra is magnified, okay, it's glorified. Because you see, this is a cat, but this is a bra, so it's waiting for something to act on, okay? So how does this operate? This is an operator, therefore. Do not confuse with this. This is a number, in fact it's 1. But if I just reverse the two things, the bra is to the right, and therefore waits for something. Let's see, Pn, you apply psi, okay? The result is phi n, the scalar product of phi n with psi. Okay? That's exactly the action. And this is what the component psi n of psi on the basis element. Psi n, phi n. Okay? So what this operator is doing is projecting for you the full vector psi into one element only. You see? I am just projecting on the n element. Pretty much as you do if I have the basis on the plane. I have here a vector v. I can write it as the x component plus the y component, okay? And somehow this object is telling you the component along x and the component along y. And in the same way, this operator here, applied to psi, selects for you the component along n. Is it clear? Okay. So these are called projection operators. Okay, given an orthonormal basis, you can form the projection operators. What are the characteristic features of projection operator? That if you square them, okay, you get the same thing as Pn. This is a definition somehow of projection. Once you project a vector, then you can apply it again, nothing changes. You have already done. Okay? the best way to see this is essentially, suppose that I have here phi n, and I apply it another time, phi n. This is very somehow brutal in some sense, but it's perfectly fine. This is 1, okay? So this is nothing but phi n, okay? Which is p. And you can make it perfectly meaningful, okay? So if you take this definition and you adopt them, you will find that it works perfectly nice, okay? So projection operators are useful, and in some sense what is written here is that this is equal to the sum over n of the projection applied to psi, okay? And the other property that you have is that the sum over all possible elements of the basis of the projection operator is just the identity, okay? So please start familiarizing with these concepts. Okay, it's very boring, I know, okay, but we have to cope with that. Now, let's try to see how to write any Hermitian operator, okay, in terms of the corresponding projection operators. Now, I want to show to you that I can always write A, if I find a basis, phi n, and the corresponding projection operator, I will be able to write the operator A as the sum over all elements, the eigenvalues, times the projection operators. Okay? Let's prove it. There are many ways. For instance, let's take A and multiply by the identity. We said that the identity is equal to the sum over n of Pn. Okay? Pn is phi n. Okay? So this is a linear operator, and therefore is sum over n of A applied to phi n. But what is this? Since this is an eigenvector of A, this is equal to sum over n of an phi n. Okay? But this is Pn. Okay? So I show this. So with the projection, okay, you multiply by the eigenvalues, and this is a way of writing the Hermitian operator. Obviously, in general, you have to be, again, as I said, a little bit careful to the degeneracy. So in general, I might have several elements all belonging to the same eigenvalue, okay? And this degeneracy index J in general would be from 1 to some degeneracy Gn, okay? This could be 1, 2, 3, whatever. Now, in general, if you want to project on a given eigenvalue, the expression I gave you here must be slightly generalized, and should be the sum over all the j from 1 to Gn of phi nj. Okay? So I have to sum over all, I have to project over all eigenvectors belonging to the same eigenvalue at an. Okay? This is the projection on the subspace of eigenvalue an. Okay? And with this small distinction, the property holds also for degenerate eigenvalues. Okay? Okay. We're almost done. I know that this is not the most entertaining discussion you can find, but we are almost done. Now, why is this useful? It is useful because it shows that you can represent any state in the Hilbert space in terms of the basis that you like most. Okay? This is the goal of somehow this rather annoying discussion. Okay, so I have a state, okay? I rewrite this in terms of the identity, and I told you that the identity is the sum over all eigenvalues of any operator you want with the Pn, okay? So I write this as sum over n, okay? Then Pn is the sum over j, or 1 to Gn, of phi nj, phi nj psi. Okay? So somehow this is the way of writing any vector, okay, into the basis of your operator A that you like most, with appropriate components. Now you realize that if psi is normalized, then you can prove it's a very simple thing using the orthonormality of this thing. So if psi is equal to 1, then you can prove that the sum over n of the sum over j from 1 to Gn of these elements here, okay, so somehow the phi nj psi modulo square has to be equal to 1. Okay? So the square sum of all components of your vector on the basis that you select is 1. Alright? Now, you presumably recall that when we worked with wave function, we imposed normalization. Okay? That's precisely the specialization of this to the case of a continuous variable where the operator A is the position operator. There is one small comment that I should make. The position operator is a bit bizarre because it does not allow you to have a discrete basis, although infinite dimensional. It is in fact a continuous basis. For every point in space, you have an element. But you might also be worried because this element is not a normalizable function. So again, this is one of those cases where there are delicate aspects related to the infinite dimensional nature of the problem. All these aspects can be solved, okay, given sufficient mathematical care. We don't really want to enter into these delicacies, okay? But that's the continuous version of this. So the integral over all possible elements in the basis, okay, which is here x, the position of your particle, modulo square is exactly 1. Okay, so in some sense, while this is the element nj of the vector psi of x, you could think of as the scalar product of psi with the position eigenstate x. Okay? This is the meaning of the wave function. Is the scalar product of the state psi on a given chosen basis that you like, which is the position eigenstate. Okay? So this somehow closes the circle. We started thinking about wave function. Now we know that this is a particular representation of states when So now you work with the position eigenstates. Okay. I think I have to almost to stop. Just let me show you a couple of simple examples that we have already seen where you see some of these delicate aspects of the story. I am almost always skipping over delicate mathematical aspects because this is not our business, but there is something that we have already seen where you can appreciate the where difficulties can hide. Let's consider a particle in one dimension. Okay? So the usual wave function of, in this remaining part, let's assume that h bar has been set to 1 by appropriately rescaling things. Okay? I don't want h bar so much. So the momentum operator is minus I, the derivative. Okay? Now, let's look for eigenstates of this. You know, it's an Hermitian operator, right? We'll see more about this. Let's look for the eigenvalues. Phi k, okay? You know how to solve this, right? We have seen. Phi k is e to the I kx, the plane waves. Okay. What is the label that I should use? Well, like here, n. Now it's a continuous label. K over the whole line. Okay. Okay. Now, consider, so this is simple. We have seen it already. Consider the following Hilbert space H0 made by function, okay, where x is in a given interval, AB, could be 0L, for instance, if you want, such that psi of A is equal to psi of B is equal to 0, and the integral of psi x modulo square is less than infinity, let's say 1. Okay? What is this Hilbert space? It's the Hilbert space of the infinite square well we have seen. I've called just A and B the two limits, 0L, whatever you want. The function goes to 0 here and there. Okay. It's easy to prove that P is Hermitian in this space. Okay? Just prove that whatever pairs of functions you have which are 0 at the border, this object is equal integration by parts to phi p psi star. Okay? Just integrate by parts and you will realize that the term that comes from the boundary is precisely 0 because the function vanishes at the border. Okay? Nevertheless, the eigenvectors of P, which are this, do not belong to the space. Okay? So you see a clear case of an Hermitian operator. P is Hermitian according to our definition. However, it is a basis of eigenvectors that do not belong to the space that we are considering. Okay? Second case. Let's consider, clear so far? Buongiorno. Let's consider a small variant of it, the Hilbert space HP, with precisely the same thing, except that now I remove the 0. I impose that the function is periodic, exactly the same at the 2 points. Okay? Again, we have seen this. Remember when we solved the well problem with periodic boundary conditions? In that case, okay, you can still prove, so this is the periodic boundary condition exercise we did. you can still prove that P is a Hermitian on this space. For the almost the same reason. The boundary term, since the functions are the same at the 2 points, disappears. Okay? This time, we can find a basis of functions for this operator here. Remember, just take k equal to 2 pi n divided by the length of the boundary, b minus a. Okay? So this is a discrete, although infinite dimensional, set of eigenvectors of P. Okay? So P, Hermitian, but in one case it has no eigenvectors in the space. In the other case, it has a discrete infinite number of eigenvectors in the space. And indeed, this is the Fourier basis of this space. Okay? Clear? So you see, depending on small things, how you precisely define the Hilbert space, things might be subtly different. Obviously, if you think of the Hilbert space of functions, psi of x, which are normalizable, so the L2, psi x, less than infinity, and such that the function vanishes at infinity, again, you can prove that P is a Hermitian because the boundary term at infinity vanished again. But this time, this object here, being not normalizable, do not belong to the Hilbert space. Okay? So, different variants of almost the same problem show slightly different things. So when I told you, careful about the spectral theorem in the infinite dimensional case, I was alluding to possible situations like this. An operator that is formally Hermitian, but somehow the eigenvectors do not belong, strictly speaking, to the space you are considering. Okay? So just think of such small, annoying cases. And you know that you can still, we all survive with plane waves, although they do not belong to the space, because these are somehow very useful in writing Fourier transforms. Okay? So for us who are, not sophisticated mathematicians, they are fine as well. Okay? So don't worry too much. But I just wanted to tell you that there could be subtleties. Just in case. Okay. I think I have to stop here because this is already sufficiently boring. So next time I finish this abstract part. I sent you, by the way, the notes. Okay. So all I said, you find it in the notes. Next time we will do the final thing, which is what happens when you have two commuting Hermitian operators. Okay. I can find the basis of common eigenvectors of the two commuting operators, and then we move to more, entertaining things like angular momentum and so on. Okay, so see you on Thursday.